All right. Well, good morning. Um, I apologize. I'll probably be coughing and so on throughout this, but I think we can make it through it. There was homework due today. I think everyone submitted something, which is great. The homework was to write a little program that took two arguments on the command line and printed out the second one the number of times indicated by the first one. And there's a lot going on here, and what you might have done was write some C code that does this. And some of the concerns you have with the C code are converting that argument to an actual int, and you can use A to I to do that. You could compile it and take a look at the compiled code. I don't know how much or how little that would help you, but it'd be a place to start. So a number of things came up during the course of watching you all work on this. One is you really need to read the instructions. You people really need to read the instructions. So I got questions about how to convert the argument to an int. That's on the slide right here. A lot of you used a completely different, well, not a lot, a couple of you used a completely different error message. Use the error message I give you because, again, I'm trying to automatically check your assignments when they come in. And it just makes it faster, and I can get feedback back to you quicker if you can do that. And name your program what it says here, hello.asm, because that would be helpful too. Help me find it. I gave you some information about command line arguments. Specifically, I told you that argc was in EDI and argv was in RSI. And there you go. I mean, I think that was, I'm hoping that was fairly clear. It was on the slide. I did advise you strongly with italics to pay attention to the callee saved versus caller saved registers. A lot of times you might be using a register and not realize that the thing you're calling is going to override it, like A to I. And so you set up your registers just the way you want them. You call A to I, and it messes up your registers because there are callee saved registers that you are responsible for taking care of, and caller saved registers that the thing you call is responsible for taking care of. And you need to understand the difference and be aware of that. But it's easy to get around that with push and pop, which is what the advice on this slide was. All right. I think we can see if we can pull this up. We can take a quick look at my solution, which is not optimal, but it's my solution. So here it is. Up at the top is my build line. I actually use the exact line out of the slides to build your stuff, so don't worry about that much. Global main, and then declare those two external. Section text, here's my main function. You'll notice that I push R12 before I do anything else. That's because I want to use R12. It's a callee saved register, and I am the callee from the point of view of the C runtime. Right? The C runtime is called my main function. And so if I want to use R12, I'd better put it back. And I do want to use R12. Right? The fact that it's a callee saved register means that if I then turn around and call A to I or call put S, they're supposed to do the same thing. They're supposed to make sure that when things come back to me, R12 isn't changed. So that's convenient for me. So I want to use R12. So I just go ahead and save it up front. Another callee saved register is RBP. So I save it. And another one is RSP. And so I preserve it in RBP. Standard stuff. Only unusual thing here is pushing R12. I could have pushed it after this. Doesn't matter that much, I guess. I chose to push it before. I check number of arguments. So I know that argc comes to me in EDI, so I just compare that to 3. And if it's equal to 3, life is good, and I'm going to jump to OK. If it's not, then I go and get an error message, and I print it. And I set my return value to 1, and I jump out. I didn't check your return values. I didn't care about that. I didn't specify anything for it, so don't worry about that. Just habit on my part. So if everything went okay with the number of arguments, I jumped to okay. Since R12 is a call saved register, we can use it to hold something like a pointer to argv, and we won't have to mess around with saving and storing it. So I go ahead and take RSI, which I know is my second argument, which is argv, and I put it in R12. That's great. So now I'm going to call A to I on argv1. So where is argv1? Well, R12 is the pointer to argv, and argv1 would be, just to emphasize this, 1 times 8 further along, right? R12 plus 0 times 8 would be the name of the program, which would be hello in this case. And so R12 plus 1 times 8 is the first argument, argv1. If you watched the video that I made on the Linux vulnerability, I spent a lot of time talking about what stuff is on the stack at the start of a program. And so you would have seen all that in that video. If you watched the video I made about the stack, then again, all this stuff is discussed in there. So those videos are in previous classes for Ireland. Let's see. Then I call A to I with respect to the PLT because I want my code to be position independent. If you didn't, that's okay. I didn't tell you you had to be position independent. I just did that. So that goes ahead and calls it, and the result's going to come back to me in EAX, right? The bottom 32 bits of RAX, because I know it returns an int. So I go ahead and I save that in ECX. That's my count register. I'm going to use the count register. The count register is a caller saved register. So if I then call something, I'd better save it first. So just keep that in mind. I then go ahead and check to see if the count that I got back is 0. Some of you checked for 0. A surprising number of you checked for 0. I'm very proud of you. You all are awesome. Some of you did not check for 0. That would be a bad thing, right? Again, think about what your C program would do if I fed it a 0 at the start. I didn't ding anyone for not doing that. But just be aware that you have to consider your entire input space. And so I go ahead and compare it to 0, and I jump if less than or equal to done. That's right. I jump if it's 0 or if it's a negative number. How about that? So some of you don't handle negative numbers well. All right. I didn't ding you for that either, but again, something to think about. So now I'm at top, and I say, go ahead. I want to call put s with argv2. Right? argv2 is the string I want to write out. And again, since RCX is a call saved register and we're the caller, we have to save it. So I go ahead and get argv2. Where is that? That's at R12, which is where I stored my argv pointer, plus 2 times 8. And I put it in RDI. There we go. That now holds the pointer to the string that's in argv2. I then push RCX, right? Because it's up to me to save it, right? It's a caller saved register. So I save it and then I call put s, and then I restore RCX so that I don't mess my loop up. And then I do a loop top. So that decrements RCX, checks to see if it's 0. If it's not 0, it goes back up here. So for example, if a count was 3 at the top, I'd come in here, do it once, decrement it to 2, go back to the top, come in here, decrement it to 1, go back to the top, come in here, decrement it to 0, stop. So I'd print it 3 times. Now I fall through to done. Done says set the return value to 0 and return control to C runtime. Again, if you didn't set the return value to 0, I'm not stressing out about it. It's just a habit. So I set EAX to 0, and that's how you best be doing it. And you'll notice, some of you may notice, I just did a straight compare ECX and 0. I didn't do test ECX. That's because I wanted to jump if less than or equal. So I actually had to do the full compare in order to be able to use that jump. All right, back to this. I put my base pointer back. Sorry, I put my stack pointer back where it should be. I restore the base pointer. I restore R12, and I return. There we go. There's my giant program. And there's my error message at the bottom. Does it work? It's always fun to see if it will. So hello by itself? Nope. Hello with 3 arguments? No. Hello with 2 arguments? Looks like it's working. Let's try it with 0. Let's try it with -17. And let's try it with 6. Yep, seems to be working just fine. So there you go. That's how I solved it. Some of you solved it in pretty much the same way. Some of you solved it a little bit differently, like you had a thing that counted up. That's fine. A couple of you did something that that was a bit convoluted, but it worked. So I'm okay with it. That's fine. That's fine. I'm just happy that you all were able to do it. All right. I was going to have a tool section for you today, but I realized that what I wanted to cover today in tools, if I added it, I would end up talking too much and my voice would give out, which it's threatening to. So I'm going to skip this. So sorry. We'll bring something in next time. Let's talk about processes under Linux. And specifically how a process gets started under Linux. So you can read about the AMD 64 ABI. This is where you're going to find the calling convention and other information. And I went ahead and linked to the document that Intel has preserved on their site. And they keep moving this document around. So a year from now, this link will probably be somewhere else. It's the way Intel does things. I don't understand. But this is a pretty useful reference. And of course, the Linux kernel has documentation. So you can head over to kernel.org, and there's tons of documentation on here about the kernel. And it's really good stuff. It's really interesting. It gives you some of the rationale and the reasoning behind why things are the way they are. And there's a lot of interesting and good stuff there, more than you could ever spend your time reading. It's a nice slide. Also of note is this. It's the beginning of a book, which has been the beginning of a book for a couple of years now, talking about the internals of Linux. And so I keep putting it up here, hoping that people will keep visiting it, that the guy will then finish it. So to start a process under Linux, you call exec VE. So in the, you may be familiar with exec and exec V. Those ultimately call here. Right? For example, if I call exec V, it will in turn call here just with my default environment. So exec VE is where this stuff comes to get started. There's a really nice resource down here, this little syscall table. And I've given you a couple links to the syscall tables, but I think this one is another nice one to know because it has the registers in it, but it also has a link to the source. So if you want to see how this is actually implemented, you can click through and look at the source code that implements the system call, which is kind of fun, especially if you're looking for vulnerabilities and things, which why would you be doing that? So you start a process using exec VE. The man page describes it pretty well. Exec VE actually knows about things like the shebang at the front of the file. It knows about a bunch of different stuff and different ways to start programs. Basically, it reads the file and then it takes some appropriate action to get it started. And once it starts a process, it creates for it a process stack. And it creates, it says a per process stack on my slide, but it's actually a per thread slide. Each thread has its own stack. And it also mentions a kernel stack. And that is true. Each thread, again, each thread gets its own kernel stack. Now, what is the kernel stack used for? Well, when you call a kernel routine, you do a syscall, then you do a context switch over to kernel space. And it doesn't use your stack because that would be bad, right? It would be potentially pushing sensitive information on your stack. And so it uses a stack in kernel space, but it can't use just the kernel stack because that's bad, because it could be pushing your stuff and popping your stuff off the stack that the kernel uses. That could be a vulnerability. So for isolation, it gives your process a kernel stack as well. And this is all done through the magic of virtual memory. So every thread has a stack in user space and a stack in kernel space. So something worth knowing. It resets the floating point control register, which we will probably not talk about in this class. I shoehorned it in the last one, and I don't think it was worth it. It's out there. Just, if you want to read about it, read about it. And then it transfers control to something. And that something, it could be your entry point. It could just jump to your entry point, do a context switch and jump to your entry point, or it could transfer control to the loader, the dynamic loader. And the dynamic loader then has to deal with everything else. How does the dynamic loader know how to do its work? How does it know? I mean, is it going to go out and read your file? It's not going to do that. How does it know what to do? The dynamic loader gets its information through these auxiliary vectors right here. So the kernel has put on the stack. So up here is the maybe a little confusing. The top of memory up here, that's the bottom of the stack. And as we push things on the stack pointer moves down. The way it is, it's an inverted stack. And so you'll see we run into auxiliary vectors right here. We'll talk about those in just a moment. We run into the environment that gets pushed on the stack. You see it pushes a null, and then it pushes each one of the environment entries on the stack. It pushes all your arguments on the stack after it pushes the null, and then it pushes argc. And this is actually a quad word. I said it's D word here, but the value is a 4-byte value. But in the 64-bit world, you can only push 2 kinds of things on the stack. You can only push 8-byte things. You can't push 4-byte things. It won't do it. But in a weird twist that makes no sense, you can push 2-byte things. Don't ever do that. Don't ever push a short int on the stack. That's craziness. Just push 8 bytes and be happy that you have a stack. All right, lots of stuff on there. Auxiliary vectors are kind of interesting. We know what argc is. We know what argv is. We know what the environment is. What's this stuff up here? Well, that's how the kernel communicates with something like the program interpreter. And they have a structure that looks like this in the 64-bit world. And if you pay close attention, you'll see there's a type, which is a 64-bit unsigned int. And then there's this union, which can only be a 64-bit unsigned int. Why is it a union? Well, there used to be several different things in here in the 32-bit world. In fact, there still are. If you go back and look at the 32-bit version of this, there's a lot of different things that can be, and they vary depending on the type. But in the 64-bit world, it's just a 64-bit thing. So if they kept the union structure, so we still have this a.un, but it's just one thing. And there's this type, ELF64 aux vector type. And what are there? There's some types, a couple of these, right? The ignore type is ignored. It entertains me a lot when people create a type like ignore and say it's ignored. I'm like, why did you do that? I don't know. Sure, fine. They already have a null, which is ignored. Then they have a few other things in here. The one that maybe is interesting is this one right here, at_entry. That's your entry point. There are more than this. These are the ones that are defined in the calling convention. There's more defined if you look in auxv.h. If you want to get one of these, let's say you just for fun, you want to go grab one of these, you can walk the stack. That's fine. But an easier way to do it is to go and invoke get auxval, which is a little user space, because again, the auxiliary values are in your stack, and user stack, little user space thing that will let you get the value of one of these auxiliary vectors. So you give it the type. It will then walk through them trying to find one that matches that type. If it finds one, it will return it to you. All right, so in summary, on top of the stack is argc. That's followed by argv. That's followed by your environment. Those are both null terminated arrays. So you can ignore argc and just plow through them looking for the null. That's fine. That's followed by the auxiliary vectors, which are also null terminated. An auxiliary vector chain is terminated by an auxiliary vector with type null and value null. So it's like two nulls in a row. Now, this is different from what we want when we start main, right? When we start main, we want stuff to be in registers because that's what the calling convention says we're supposed to have. So we want, like it said in the homework, we want argc to be in RDI and argv to be in RSI and E and VP to be in RDX. That's what the third argument goes, right? It's not, if you think it's not logical for it to be RDI, RSI, it's not. It's just the random order that they're in. So if you're starting a program without the C or some other runtime, you might have to worry about this stack stuff. This is foreshadowing, by the way, for you. It's foreshadowing. May need to worry about that at some point. So we can look at the stack. That can be fun. I have a little video that talks about this. And I've also got a, let's see, there it is, a little program, view stack, which you can take a look at. It's got some interesting stuff going on in it. It's got macros, lots of stuff happening in here. So lots of crazy stuff with curly braces. Who knows what all's going on in here? If you run it, we'll pipe it to most. It goes ahead and tells you what's on the stack. I didn't add any command line arguments. Let's go ahead and do that. Let's add some command line arguments. Let's say one Fred. A specific Fred, and there we go. Let's do that. So when I run it now, it tells me here's where the stack pointer is located. This will change because, again, address space layout randomization, and the little view stack is a position independent executable, so that will change. It goes and gets argc, and it says in this case argc is 4, which makes sense. I gave it 3 arguments plus the name. What are they? If you look down here, there they are. Here's what's in argv. So what are the top items on the stack? So here's the stack from the position 0, which is at start, which is argc, which is 4, followed by a bunch of stuff that points somewhere up in memory. That is the argv array, right? Remember, the argv array is a char star star. It's an array of pointers to character strings. So each of these things is a pointer to a character string. And there's the null terminator for that array. That's followed by the environment array, which is, again, pointers to character strings, and that keeps going. So here's what's in argv. Here's the offset. This is RSP plus 8. This is RSP plus hex 10, which is 16. RSP plus hex 18, which is 24, and so on. And there's the string that's there. And there's the terminating null. That's followed by the environment. And the environment goes on for quite a ways. So if you wanted to go find something in the environment, you could walk through this and look for example, a shell or so on. That's how Gideon V works, which is why it's regarded as not a super efficient thing to do. So there we go. Null terminated for the environment list, taking us through the auxiliary vectors. Yay, auxiliary vectors. And so we walk down through them, and you can see there aren't that many of them, and they're terminated by that null I mentioned earlier. And that's it. That's what's on the stack. And that program is available up on iLearn as well. You can go and see what's on the stack if you're curious about it. So let's say that instead of doing all that, you want to write a main program. How does your main program get started? And this turns out to, weirdly enough, kind of be important because sometimes it's hard to find main. And let's pop out here for just another moment. And let's go ahead and take a look at one of the files in the system. Let's look at What's a good program on the system? LS. LS is pretty simple. We should be able to make sense of it. All right, so you're going to do some reverse engineering. You should be able to reverse engineer the stuff on your system. So here we are in LS. Let's head over to main. Text domain. That's not it. That's part of the PLT. It's still part of the PLT. That's calling something in the PLT. So is that. libc start main is not, I don't know what that is, but that's not our main. That's it. There's nothing that has the label main. How about underscore start? Oh, there's gmon start, but that's not what we're looking for. libc start main. That's it. So that's not super helpful. So if we look at LS and we start poking around trying to find what things start, there's no start symbol and there's no main symbol. It has been stripped. There might have been at some point, but there's not now. But it has to have an entry point. So let's find the entry point. And we can do that in a number of ways. The simplest way is to go ahead and look at, man, I can type this morning, to just run readelf on it and say, give me the file header, and right down there, look at that. Entry point address. There it is, 67D as in Delta 0. So if I go back into it and I look for 67D0, it takes me here. Let me scroll up just a little bit. So it takes me right here to this guy, which is nice. It shows me that it's probably a correct branch target. So I probably got that right. And that's followed by some code that does some stuff. All right. It's preceded by some code too. It's not the first thing in the file. It's just the entry point. So we can go get the entry point by using readelf. You could go get it by using the auxiliary vectors, but we're not running the program, so we can't do that. If you wanted to, it would be of this type, which is 9, and you can just go get it. That's in fact how the interpreter goes and gets it. So we disassemble the entry point, we see this. This is what we spot at the entry point to LS. And an interesting question is, what is this? Right? This is a reverse engineering class. Let's reverse engineer it. What the heck is all that stuff? Right here, this last call keyword pointer right here. If we, where'd my little thing go? There it is. If you come back here and we walk down through it, the disassembler has happily gone ahead and told us this is __libc _start _main, which is an external symbol. That's why we get to see it. That comes out of glibc, so it's dynamically linked. So this is probably pointing to an entry in the PLT that in turn points to an address on the GOT, which points to here. And objdump has figured that out for us, which is nice. So what is libc start main? Well, if you go and look it up, which you can, you won't find a man page for it, but if you go online and look it up, you'll find it. It's part of the Linux standard C library. This is how you start the C runtime, or how it starts itself, basically. And so you'll find it, and it has this function prototype. The first argument is a function pointer. This is how you write a function pointer, right? You write the function. So we write like main int char star star char star star. Then you put the function name in parens, and then you put a star in front of it. And there you go. That's how you write a function pointer. So you write the function prototype, you put the name in parens, and you put a star in front of it. There you go. So this is a pointer to some function, which it happens to call main. Seems like that's our main function. Great. So libc start main will start our main function for us. It needs argc. It needs argv. That's a weird looking name. This is a type of notation that was really common for a while. I'm not going to go into it. People used to name their variables things to indicate their types. It's a pretty common thing, like SZ for a zero terminated string. You'll see that throughout parts of the library because some people like using it. Don't worry about it too much. This is really argv. Then there is an initialization function. There's a finalization function. And there's this thing, which is the finalizer for any dynamic library stuff. And then we need a pointer to the end of the stack. And once you have all these things together, you can pass them as arguments to libc start main, and apparently it will start your main function. It'll set some stuff up, build your stack, do what else it has to do, and start your. Actually, it won't build your stack. Linux has already built your stack. Sorry, it'll set up stuff for you and then invoke it. You can go and walk through it with the debugger if you want to know what it really does. So we can map all of those thanks to the calling convention to registers. We find out that this should be an RDI, that should be an RSI, RDX, RCX, R8, R9. We've used up the 6 registers we have for pointers and ints. That's a pointer, so it has to go on the stack. So in the strangest twist, the pointer to the end of the stack has to somehow end up on the stack. It's what it says, okay? It's what it says. So if we look back at the AIM64 ABI, we'll see that it does in fact specify all this stuff about the stack in it. Here's the initial process stack. It says, oh, you've got to have an argument count and the pointers to the arguments, and you've got to have a null and environment pointers followed by a null, auxiliary vectors, a null auxiliary vector. There could be nothing here. I don't know what that could be. That could be, who knows. Then an information block, including all the stuff that this stuff points to, right? These are pointers to strings. Where do those strings live? They live up in here, along with some other stuff, which you can go poke around if you want to know what all is really there. There's lots of weird stuff there. And then there's more unspecified stuff up above it. So that's what the stack looks like. And that's in fact what you'll find if you go and look at it. Linux is pretty faithful to this. At process entry, the following registers have a defined value. The rest of them don't. They could be anything. In the Linux world, they are mostly 0, but they don't have to be. What we do have to have is the base pointer. The content of this register is unspecified. So it says it has a specified value at process entry, and this tells you it doesn't. It doesn't have a specified value at process entry, but they want you to know that you're supposed to set it to 0. So one of the things we want to do is set the base pointer to 0. Can the base pointer ever be 0? No, right? The stack would have to cross through your code, which would be a bad thing, for the base pointer to arrive at address 0. Remember, the stack is at high memory, so the base pointer is usually going to be some really high value. So the fact that the base pointer is 0 is an indication that you need to, it's not valid. It's not a valid value. So we set it here to indicate to whoever gets called, the base pointer is not valid and they should set their own. The stack pointer holds the address of the byte with the lowest address, which is part of the stack, right? It points to the low byte of the last thing on the stack, the thing at the top of the stack. It is guaranteed to be 16-byte aligned at process entry. If you want to use certain library functions, printf being one of those, you will have to at some point align the stack on a 16-byte boundary. That can be a little tricky. We'll talk about it at some point. For right now, just remember that this is just going to hold the stack. And RDX is a function pointer that the application should register with at exit. Okay. What is this BA-OS? BA is the base system. Sometimes you'll see BA-OS, the base operating system. KE is the kernel extension. Again, nothing you should worry too much about this unless you're really into building your own OS. But that should be 0. That should just be the stack, which it already is. That's fine. And this needs to be this thing we call to terminate. Okay. So back to here. RDX contains the address of the destructor function for the dynamic linker. Or it might be null. If there's no dynamic linker, we don't need to do anything, right? And so it could be null. That's this guy right here. So that can be null. We know the base pointer, let's go back here. Base pointer should be set to 0. Look at that. First thing this code does is set RBP to 0 by zeroing out the low 32 bits. So RBP is set to 0. So we get that. the stack contains argc, argv, and envp. Argc is on the top. So this is the way things are when we arrive. When we arrive at this code, RDX is set this way. The stack contains this. And then we do the thing we're supposed to do. We zero out this. And when we get to main, we want this stuff to be true. So let's see what happens. Let's go ahead and try to connect what's happening in here before the call with the stuff we learned from the calling convention over here. So R9, so we take RDX and move it into R9. Why do we do that, right? This holds the address of the finalizer for the dynamic library. It's one of the only things we know. And that is this argument to libc start main, which happens to be R9. So we need to put that in R9 before we can invoke this. If only it had been the third argument, we wouldn't have to do that, but it's not. So we got to move it to the right place. And so we move it into R9. Hopefully that makes sense to you. We pop RSI. What the heck? So we take the thing that's on top of the stack, which is argc, and we put it in RSI, because RSI holds the second argument to libc start main, which is argc. And argc is no longer technically on the stack. We popped it. We then take the stack pointer and we put it in RDX. What is that about? Well, what's the thing? Once we've popped RSI, the stack pointer is now pointing at the first entry for argv. And we put that in RDX, which is the third argument, which is the argv array. All right. Now we do this. What does this do? And RSP with all of this and a 0 in the last position. This aligns the stack on a 16-byte boundary. So the low 4 bits are zeroed out by this. Often in actual assembly, you will see and RSP and -16, because it turns out this is -16. All right, so we've aligned the stack on a 16-byte boundary. That's nice. And then we immediately push something. So we push RAX. What's in RAX? We don't know. It's some random stuff. We absolutely don't know what's there. There's nothing defined in there. Why do we push something undefined on the stack? Well, this messes up the alignment, but that fixes it. I don't know why they do this. They could have just pushed RSP twice or pushed something else, but they chose RAX. So they push RAX so that when they push RSP, the stack is again on a 16-byte boundary, right? This pushing RAX here subtracts 8 from the stack, so it's no longer aligned. And then pushing RSP subtracts another 8, so now it is. So that results in RSP being the last thing pushed on the stack and it being aligned on a 16-byte boundary. And you'll notice that we did say this guy had to be on the stack. The end of the stack had to be on the stack. That's how it gets there. Just how it gets there. R8 gets this, which happens to be a pointer to Finney, which is a little function defined by the C runtime. It's really a stub function that you can use. And if you're of a malicious bent, it's really useful. It's basically a finalizer for your program. And you can, by default, it does nothing, but you can do stuff with it if you want to. This is the address of init. This is an initializer for your program provided by the C runtime, which again is a stub that typically contains nothing, but you can modify it if you so choose. And so those go into R8 and RCX because R8 and RCX are the places that hold those arguments. Finally, look at this. We load RDI with this RIP relative thing. And that is the RDI is the first argument. So that's the address of main. So there we go. We load the address of main into RDI. And then we call libc start main. And then there's this halt. So what is the address of main? Well, we know right here for this instruction at 67 Fox 1, RIP holds 67 Fox 8, right? It points to the next instruction. So we take 67 box 8 and put it here. This is a negative 2's complement number. And so you could put it in Python maybe and have it convert for you. That'd be fine. If you're a strange person like me, you can do it in your head. We know that we would be subtracting this for 2's complement. We'd be subtracting from basically all f's and a 0. And so 0 minus 8 is 8. F minus f is 0. F minus 5 is a, right? 16 minus 5 is, and so is, and then, sorry, 15 minus 5 is 10, which is a. 15 minus e, right? F minus e is 1. F minus f, that's all zeros. There we go. That's our displacement. Boom, that's a negative number. So we subtract 8 minus 8 is nothing. F minus 0 is f, 7 minus a. I can't do that. I got to borrow, so that's 5. I add 16 over here. 16 plus 7, 23 minus 10 is 13, which is D. 5 minus 1 is 4. There's my result. There's my address, 4DF0, which conveniently again, see if I still have it in here. Conveniently again, the disassembly will just show that to you. So if you don't feel like doing all that math in your head, there you go. I just do that to show you that it is in fact how it works, and you can figure it out that way. So it does work. 4DF0, that's main. We found main. And this is what you've got to do often to figure out what the heck is going on with the program. You have to go in and find main. All right. So this call right here is followed by a halt. This is a privileged instruction, which we talked about before. We wrote some code that tried it, and we got a processor exception. Right? And it's a good thing we did. If we didn't get a processor exception, it would have halted the processor. That would have been bad. So this would generate an exception. We don't want that. So it must be that this call right here never returns. And it doesn't. This call will go ahead and arrange for init to be called. It will arrange for our main function to be called. It will arrange for fini to be called. And it will arrange for exit to be called, right? The exit syscall happens in here. So it handles all that for us. And along the way, our main function gets invoked. So what's that main? So let's go back to here, 4DF0. Let's go ahead and look for 4DF0. It's above where we are, so we have to go backwards. There we go. And there it is. There's our main function. Start. This is a good indicator that we've hit the right place because we have the branch thing. There's nothing special about it, right? You can see that it sort of begins sort of in media res, and there's no label for it. There's main. And it begins to do the work of doing ls. And if it were me looking at this, I would immediately find my eye drawn to this. And I'd be like, ooh, sprintf, what's going on there? Ooh, set locale. That looks like something I might be able to use. And then you'd sort of walk through it and you do the general process of reverse engineering. All right, so there we go. This is what's there. We're not going to dig through reversing ls. Now you know how to find main. That's pretty important. So how did this get there? How did this code that the people who wrote ls did not write, and if you look at your program, which has a main, you'll see it's in there too. How did that code get into your code or into ls or anywhere else it shows up? How did it get there? Excuse me. Well, it got there thanks to this file, crt 1.0. There's a little .o file, that's because there's 3 of them, that live in lib x86 64 Linux GNU, and there's crt1, crti, and crtn. There's 3 little object files. And they are linked with your program in a specific order, right? The order in which you link things matters. And they are linked in a specific order with your program. And so let's pop out to here, move to the side a bit. And let's go ahead and, if I can type lib x86 64, there we go. And what's in here? Whole bunch of stuff, whole bunch of things that have to do with the implementation of these libraries on here. But in particular, there are these little .o files. and they have relocations in them. And you'll notice that this one, CRT 1.0, expects to find main. It wants someone to link it with something that provides main, and that would be your code. Once it's linked, that would then, the linker would go ahead and fix up this so that it points to main. And we see that it's doing it via the GOT. So again, this is going to be linked. It's going to put an address on the GOT, and there you go. It also needs a libc start main. Somewhere somebody needs to provide that. Turns out glibc provides that. So it's linked with both of those, it's fine. It wants an init and it wants a fini. We'll see where those come from a little later. And there you go. Oops. Well, what's happening here? Oh, there we go. I think I lost the connection for a moment. Can folks hear me?
Yep.
Oh, good. Looked like I lost the network or something for a moment there. That was weird. So let's go back to obj dump. DM Intel CRT 1.0. And there it is. That's all that's in it, right? That's it. That's the whole thing. It has this code, which you saw at the start, and these addresses get fixed up by relocations. And that's it. Call and then halt. And what's in the other ones? Well, let's take a look in I, and we'll see that it has init and fini. Here they are. And what's in, strangely enough, it also has some stuff that goes in the init and fini sections. So we'll come back to this. I think I won't have time to get through it at the class this time, but my voice will give out. But we'll come back to that at a later time. These assemble the initialization and finalization functions and allow you to add code if you want. All right. So that's where that stuff comes from. It comes from those pieces, and CRT, that's the C runtime. And there it is. In case you're wondering where it came from and how it got there, that's it. Init and fini, there we go. All right. This is a good place to take a 5-minute break because my voice is about to give out. So let's take a 5-minute break and I'll see you back here shortly. Assembly programming is very, very different. And reverse engineering is a somewhat different set of skills as well. And it's difficult to teach either one without until you've hit some kind of a critical mass where you understand enough of the system and how it works, and enough of the various choices that have been made in building it, that you can then begin to understand how pieces fit together. And sadly, that requires quite a bit of introductory stuff, right? I mean, you have to understand the calling convention. You've got to know about the registers. You need to know about weird stuff like how the C runtime starts, because when you encounter a new program that comes to you out of the blue, you've got to figure out where the thing starts. And it may seem weird, but most people still write their malware in C. And so you can go and look for main that way. Sometimes they obfuscate that, so you have to know how to sort of chase that down. But these are things that you have to sort of figure out. One of the challenges to doing all of that is just finding the program itself. That may seem a little weird, but there's this challenge sometimes of just finding the code. And bad actors are going to do everything they can to try to hide what they're doing. And you've got the code, right? You have the binary. You can disassemble it. So they have to find a way to hide in plain sight. And so we're going to look at a little bit of that now. So let's look at some control flow stuff. So I can disassemble your code, but maybe you don't want me to. So how can you stop me from, I mean, I've got disassemblers. I have Ghidra and ObjDump and a ton of them, right? The online disassembler. I have somewhere I've got old versions of other disassemblers. Disassemblers for other platforms. How are you going to stop me from this? You can't stop me from disassembling your code, but you can you can do a couple of things. And they range from making the disassembler mislead me, just kind of the least malevolent, to, and I'm not making this up, to people who have written stuff that exploits a weakness in the disassembler to take over the disassembler during disassembly. Because that's a thing. It's just software. It's got bugs in it. If you aim it just right, you can do that kind of thing. And yeah, I won't pick too hard on any particular disassembler, but that's the thing that's happened. So anti-disassembly is this collection of tricks and techniques, and we'll talk about a few of them here, not that many. There's a pretty good article online you can find about it that will give you some other details. And the basic idea behind anti-disassembly is to confuse the analyst and the tools and everybody about what the heck's going on. Right? The computer's not confused. The computer just grabs instructions and executes them. And the state of the machine at any given time, that's the truth. And everything else, right, the state that the machine reports to you, that might be misleading or just wrong. What the disassembler tells you, what the compilers tell you, any of that stuff could just be a lie, right? The machine state is the truth. You got to get as close to the machine state as you can if you want to know what's going on. And we tend to treat object code as if there's a static control flow that is explicit. And that's not necessarily true either. Neither one of those is true. It's certainly not true that the control flow is going to be explicit, right? Assembly is already hard enough to read. But I can use the tools of assembly to make it so that I've obfuscated the control flow. So it's not what it looks like when I look at it in a disassembler. It's in fact something else. And it doesn't have to be static, right? I can ramp things up and use computational techniques to change my control flow at runtime. I just can do that. And most disassemblers, right? This is the problem people have known about for decades. Most disassemblers assume an address should be used only once in a listing, right? An address contains a byte. Fine, got that. And that byte doesn't change. Okay, it doesn't now because we have memory protection, but in the old days it could. And in fact, on some other platforms, it can. But we'll assume it doesn't change. Well, that's where my code is. Well, not necessarily, right? That byte could be could be an opcode, a prefix byte, part of an argument or an operand for something. And it might be any of those during the course of execution, depending upon where the instruction pointer ends up. So all these things complicate the control flow, right? I look at a program and I say, there's my program. Oh, look, it's got this loop and it's got this branch, and that's what it is. But in reality, it's putting stuff on the stack and using return-oriented programming to compute a control flow that's not evident to me at runtime. So lots of ways things can go very bad. So linear disassembly is, the practice of just grab the bytes and just start disassembling them, right? The processor is going to fetch these bytes and decode them. And in fact, it will, right? It'll go ahead and grab this and begin decoding it. And it will grab this and begin decoding it, right? And it will grab this and begin decoding it. It's always in this process of blind speculation. The processor is always trying to do as much stuff in parallel as it can. And most of what it does gets thrown away. And so it grabs the byte starting with EB, the byte starting with FF and with 31 and with C3, and it begins to interpret all of those. And when it realizes that this is a jump instruction, it knows it can throw away the rest of the pipeline and figure out this jump. So the disassembler says, that's how the processor does it. I'll do the same thing, except I won't do the crazy parallel stuff. I'll figure out this is 2 bytes long, and I'll say this is jump -1. I'll figure out this is an XOR, and I'll write that out. So here's what a linear disassembly gives you. It says jump -1, and then this XOR. There you go. Linear sequence of bytes yields a linear sequence of instructions. What could be simpler? That's how objdump works. That's how all these things work. It's even how Ghidra and really fancy ones work. They try to do some clever stuff, but at the end of the day, they're just trying to disassemble this stuff in sequence. If you ever used Ghidra or you've used IDA Pro or something like that, you've analyzed malware, you spend a lot of time going in and saying, no, that's a data byte, and no, go make code here and reinterpret it until you can get something that you can analyze. Here's our linear disassembly again. It's written horizontally for convenience. And you see this says jump -1. What does that do? Sorry. Well, we know the instruction pointer points here, right? It points to the first byte of the next instruction in sequence. So RIP is pointing there. So if I add -1 to that, I wind up there. So my jump -1 takes me here, and I reinterpret this FF as an instruction. Now it's not this was the operand to the jump, right? FF is -1 in 8-bit 2's complement. But now I'm interpreting it as an opcode, and it's push. And I'm pushing the thing pointed to by RCX onto the stack. Okay. And then that's followed by return. So this might occur in the middle of a program. We do some computation, we get a value of something. I push it on the stack and I return. And the return is not evident up here, right? This is part of an XOR. But now that I've changed the control flow, it gets reinterpreted as a return, right? Because for this instruction, RIP points here. After this push, it'll do the return. And so this bails out of a function early and gives me back some information. And it's not evident from looking at the disassembly immediately. That's what it does. So this is kind of an odd little trick, but it's not the only one. This is not original to me. I found this, I think this comes out of a talk on anti-disassembly that I saw many years ago, and I made a bunch of notes, and I've just drug it around ever since then. There was an error in the original presentation, which I fixed, so but I can't remember where I got it from, and so I can't cite it directly. I feel bad, but it's still a really good example, so I like to use it. So here's a linear series of bytes, and they are moving a value into AX, zeroing it out, a jump -6, that's suspicious right there, followed by call. So this instruction executes, RIP points here. That instruction executes, and RIP points here. This instruction executes, RIP points here, and this says -6. Okay, RIP is pointing here, so we go 1, 2, 3, 4, 5, 6. There we go. Or if you like to count backwards, it's FA. So F, E, D, C, B, A, and you're here. Either way. So whatever, how you want to think about it, we jump back to here. And this then says, EB05, jump forward 5. Okay, this is like one of those little games. So RIP is pointing here. We want to jump forward 5, right? 1, 2, 3, 4, 5, right? And here we are. We've bypassed this E8, which is the opcode to indicate a call, and we've fallen into the real code right here. And so whatever starts here, we're off by 1, is the real code that it gets executed. So there we go. Now we're executing the real code as opposed to all this funky stuff up front. So there you have it. We can make this arbitrarily complex. And in fact, you could go and build a tool, which people have, to look for these kinds of gadgets and build them. And it's strange and wrong, but people like doing this kind of stuff, so they exist out in the world, and they give you back this really bizarrely obscure code. Can you actually write and assemble code like this? Sure you can. Of course you can. So here's some NASM that builds that code, right? This is some NASM that will build this stuff at the bottom. There's a couple things to note about it. One is this says -6 and that says -4. The heck's going on here? If I just say J0 -4, NASM will try to fix it for me. NASM will say, you know what? I know what you probably mean, and I will fix it for you, and it'll be wrong. So I can't say JZ -6. So what I do instead is say, take my current location and subtract 4. Well, the current location is actually the location of this instruction. Whereas what I really want is the location of the next instruction, -6. So since this is going to be a 2-byte instruction, it's just -4. Just a weird thing you pick up in doing this stuff. So that takes care of that. And then what the heck is that? Well, I want to write my code just directly, the hidden code right away. So I just go ahead and put the opcode for the call right here, and then I just write my normal code. And this is going to come in and be seen as a call, and it's going to misinterpret all this. And there you go. So you can put that through NASM, and out will pop this example here at the bottom. If I put the result through objdump, here's what I get. So there's that move into AX, zeroing out EAX, jumping if equal to, what is that? That is address 2. That's up here. It's right here to this EB, just like we intended, which then gets reinterpreted and the whole thing jumps around, and the code that executes is not here, right? This says call something, an add. So that's not right. So objdump just straight up gets it wrong because of course it does. Now this kind of code isn't likely to really fool anybody too badly, right? I mean, you'll see this and look through it and wonder what's going on, but you'll pretty quickly catch on that this is not one of these addresses over here in the column, and you realize that they're playing this trick, and you can go through and fix it. But you notice it's not immediately obvious over here in the listing, right? You'll see lots of JE and some address, and this is just JE and an add, in this case, an offset. So, and once you've fully linked it, it would be an actual virtual memory address. And so it'd be some long thing, and it says, oh, it's this plus an offset, but that doesn't tell you anything much. And so it can hide there for a while before you realize it. Once you realize it, it's not that bad to sort it out. And tools, lots of tools will see this and they'll say, oh, you know what? I need to disassemble starting at this address. Ghidra, for example, will do that. Ghidra will say, I was told to disassemble here, but I also need to disassemble here. And so it tries to make decisions about how it can handle it. And it's fairly good about doing that. But I can make things worse. One of the things people will mention, Dr. Reverse Engineers, they'll talk about dealing with things like push jumps, push rets, and all those kinds of things. So let's walk through this code and see what's happening here. So here we go. I get dot there, get the address there. That's here. Get the address and put it in REX. And then I increment REX. And then I push it on the stack. And then I zero out EAX for some reason, and I return. Where does this return go? Well, it goes to what's on the top of the stack, which is REX, which is 1 plus the address of there. So this return is really a jump over this weird data byte to here, which then puts 16 AL, 17 EDI, and does a syscall. So it exits with value 17. So there you go. I did a push return. Push return is annoying, but it's perfectly valid, right? The thing on top of the stack is where you go. Push return is like a jump. And I did some math with it. I could have made this math crazy hard as long as I got the right answer. And in fact, I could have done math that gave me effectively a lookup table. There is a piece of code called VM Protect, I believe, which uses a collection of routines that all implement the same thing, but in different ways. And at runtime, it basically randomizes and generates a random address and then jumps there. And that's going to be, or through a lookup table, that's going to be one of those routines, and it's going to do the thing, but it's really hard. It's painful to suffer through it. We had to write some Python code to reverse engineer that. Wrote it all up. It's in the CERT research journal. It's fun stuff. So then there's also push return. Push return is gloriously devious. I push A on the stack, I push B on the stack, and I return. Where does return go? The push return, we've sort of agreed, is like a jump. So this is like a jump to B, except I've got A on the stack. So it's really more like a call B followed by jumping to A. Right? You have to draw pictures to figure this stuff out. Push jumps are super common. In fact, compilers will emit push jumps, right? I push a value on the stack and then I jump. And that results in the thing I jump to being able to return back to the address I pushed on the stack. This is just the way assembly works, okay? Making your control flow non-obvious. This is not a lot of code. This is a little short program. You can put it in, it runs, it results in 17. You can put it through Ghidra. So I put it through Ghidra. Here's Ghidra. Ghidra gets completely buffaloed by it, right? It sort of sees the first part and then it's lost. And it does do a pretty good job of figuring out what gets pushed. It says, you know what? It's actually this address that gets pushed. I'm not sure why it's getting pushed. I'm going to break it out. Here it is. I don't know what's there. So you could go and make code here and it would be fine. But Ghidra does get broken. And in fact, the decompiler in Ghidra, which is a little more robust, also gets broken. It has no clue what's happening here. Even if I make code here, Ghidra is lost in this one. You have to work hard to get that untangled. And you can imagine, I can make these as complicated as I want. And I really can. Trust me, I can make these things really complicated. And there are tools, like anything. If it's hard to do it by hand, fine, I'll build a tool. Right? Why spend an hour doing something that you could spend a week automating? So there you go. Things can get really nasty, right? Security tends to rely on some point, somewhere, somebody playing by the rules, right? Even in big organizations, you typically have security personnel, and you kind of depend on those people playing by the rules because they have access that could allow them to do some bad stuff. Organizations tend to monitor those people, and they tend to monitor each other. That's good, but again, they have access in ways that requires that they play by the rules, or you violate the security. The same thing is true for like calling conventions and everything else, right? The rules can be explicit or they can be tacit, they can be assumed. And you don't have to honor the rules. You can just pretend you're honoring the rules and then do something else. The stack is just basically unprotected memory, and you can play around with it all you want. There are things there to catch you. There are, as we talked about in the in one of the supplementary videos I uploaded, I think the one where I talked about railroad, relocation read only. There are stack canaries. You can add a stack canary so that someone who's really trying to mess with your stack, you might catch it. You have a chance of catching it. You put a random value on the stack, and then you confirm that value later before you return. And if that value is different, you immediately throw an exception and halt. That's great. That can catch malicious stuff and prevent bad stuff from happening. But again, you can mess with this stuff. The instruction pointer is really just another register, and you can modify it in various ways. The easiest way, right, is to push it on the stack with a call, modify its value however you like, and then put that modified value on the stack, and then pop that value off the stack into RIP with the return, right? You can think of, instead of thinking of call and return as dealing with a subroutine, just think of them as what they are, modifying RIP in various ways. There you go. So push return, call pop, that's a fun one, right? You call something and it immediately pops off its return value and does something else, fine. There's something called structured exception handling that I will not go into because it's way too painful. But you're welcome to go and look at that if you like as well. Tons of other stuff out there. So let's go back and think about control flow a little bit. All right. So here's some code that comes from the Linux kernel. Actually, I think it's from a device driver. And nothing too terribly interesting about it. It's C, but you'll notice it's full of go-tos, right? If the pre-allocation shrinker fails, gotta fail. If I can't get the least recently used memory, fail. If I try, this next one, can't get an inode, fail. Otherwise, I made it through return S. So I check for these bad situations and I go to fail. And fail says, destroy the unused super block and return null. So a little piece of allocation here. Here are these little go-tos. Just the way they wrote the code in Linux. Here's some more code out of the Linux kernel. You'll see, we go down through here, there's a continue that jumps to the end of a loop. Here, what are we in? We're in some kind of an implicit loop. Continue, what's that gonna do? Think about that pretty hard and go back and read. We have a go-to down here, go to retry, which takes us up here to retry from in the middle of this nested code up here. So there's stuff like this throughout it. And you've probably been taught in your computer science classes that you should never use go-to. And I'm here to tell you that go-to is all over real code. It's there. It's used a lot. And why? It's often used to avoid this kind of code. This is what is colloquially known as arrow code because it looks like a little arrow, where I end up with this sort of deep nesting. And when I have something that doesn't have exception handling, like C, and I have lots of exception cases, I can wind up with very deeply nested code and to handle all those exceptional cases. And if they are independent of one another, I could have to check, check C here and then check C again down here and check it again, and it gets fairly complicated. So this is a typical reason it gets used, right? I do something, I check for an error. If there's no error, I do something else. I check for an error. If there's no error, I do something else. And then I check for an error. If there's no error, I'm done. Otherwise, I have to undo the stuff that I did in the right order. So I end up with code that looks like this. In the Linux kernel, this example, almost verbatim, shows up several places. I do this, right? So I still have to undo things in the right order, but I use goto to get out of it. Which one of these is better? I don't know. What do you like? Does the error code offend you? It doesn't really offend me, but it really bothers some people. Does this bother you? The challenge to using goto, if this makes the code simpler and to understand and easier to maintain, then it's great. It's great. And you should absolutely do it that way. If it makes it harder to find problems in the code and harder to maintain, it's wrong and you shouldn't do it. You should do this, right? You sort of have to choose the right tool to get this done. People are often surprised to discover that a lot of commercial software has these go-tos in it, especially in things like device drivers in C. And that's, again, because C likes exception. You won't find them as much in C++. You'll find it in badly written C++, but usually in C++, people have handled exceptions in a reasonable way. I keep saying C doesn't have exceptions. C has exceptions, but I don't want to get into it. It has set jump and long jump, and I don't want to play with those right now. So I'll leave you to deal with that. All right. So the kernel's written in C, so it doesn't have exception handling, and gotos can simplify the code. But this code advantages advantages for analysis that this code does not. And that is important. That's an important point. it may be that it's that it's easier to analyze this code than it is to analyze this, because I can analyze, for example, this little if by itself. I don't need to refer to any other code. And then this little sequence, I can analyze by itself. And this if, I can analyze by itself without referring to anything around it, and so on. The idea is each one of these structures is independent of the other ones, and I can analyze it by itself and understand what it does. Over here, that's very difficult. I have to understand this entire block to know what's going on, right? I have to really stare at it to see where it is. This is all strongly coupled. This is not. All right. Flow graphs. A flow graph is just what it says on the tin. It's a graph of the flow of your program. The vertices are program nodes, and the edges indicate program run ordering. Now, I've just gone through a whole thing explaining that that can be non-obvious, but bear with me for right now. A function node is going to do some operation, right? Function node looks like this, little block we can represent with an F. You come in, you do something, and you go on to the next thing. That's it. Very simple. A predicate is a little different. You come in, you evaluate something, you don't change anything, but you evaluate it, and then you either go on to one location if the predicate was true, or you go somewhere else if it was false. Very, very dumb, simple stuff. But from these two little pieces, you can build much more complicated stuff, like this little while loop over here on the side, right? That's built out of one little predicate node and two little function nodes. That's it. And I've drawn some lines and that connected them together, and that's it. So here's my little while loop. So this is a really simple way of thinking about the flow of programs. A little function that just does something and goes to the next thing, or a predicate that chooses among two alternatives. Most assembly instructions can be classified this way, right? This guy, repeating a move of bytes, it may look like it's got a loop to it and it's got some conditional checking, but really it's basically just a single instruction. It's going to do its thing, whatever it is, it's going to move something, and then it's going to flow to the next instruction. So it's just a little function node. Complex one, but a little function node. This is a little predicate node, right? I'm just going to check to see if ECX is 0, and if it is, I'm going to go here. If it's not, I'm going to flow to the next thing after it. There you go. So false is the next thing, true is here. They don't all fit in that category very nicely. This one doesn't fit that way. What does loop NE do? Well, it first decrements RCX, and then it checks to see if the not equal flag is set. Checks to see if the 0 flag is clear. And it checks to see if RCX is 0, and it branches based on that. So it's more like a combination of a function node, decrementing RCX, and then a predicate node, checking if RCX is 0, and also checking the 0 flag. So there you go. All right. With that out of the way, we can now draw programs, which is good. Well, diagrams like this should make sense, right? Predicate node, function node, lines connecting them. I'll draw these little circular connectors because I like them. So just accept it. A proper program is a program that meets certain criteria. A proper program has a single entry point. What I mean by that is control flow enters the program at a single place. Okay. Your code has a main. Control flows into your code through main. It comes into main. The instruction starts executing there. Single entry. It has a single exit point. That means control flows out of the program to a single destination. At the end of your program, you return to the C runtime. If sometimes you return to the C runtime and other times you just straight up exited, that would be two different destinations on exit, right? You might have If you have hundreds of places in your code where you return to the C runtime, doesn't matter. You're flowing out to a single destination, back to the C runtime. Doesn't matter that there's 100 different returns, it's still a single exit. Hope that makes sense. On the other hand, if I flow out to C runtime or I flow out back to Linux, that's two different destinations, and that would not be a single exit point. So single entry, single exit. And for every node in the program, there's a path from entry to exit that contains that node. In other words, there's no unreachable or trap code. I don't have a little block sitting off by itself over here that's unreachable, or I get to it and I can't get out of it. So a proper program, like this guy right here, which is the flow for this guy right above it, has a single entry, has a single exit, and has a path through everything in it. There we go, just straight through. A proper program is basically a single function. And they can contain other proper programs, and this one does, right? So for example, this little guy contains this little if then else, or if then right here. So we can identify that and say, oh, look, there's a proper program. Single entry right here, single exit right here, and path through everything. And I can draw this little box around it and say it's a proper subprogram because I cut a single exit and I cut a single entry. There you go. The result is a composite program. I composed it from this little if-then and this larger sequence. But this if-then and the sequence, these other things, composed it together and got myself a program. And that's how you build programs. There you go. Well, one more notion to throw at you, a prime program. Suppose I have a proper program that contains no other proper subprograms other than itself and single nodes. That's like saying I have an integer that's only divisible by itself in 1. In this case, these three guys at the top fit that description. I can draw a line around the subprogram, but it consists of a single node. Over here, same thing. Here, yeah, I can't do it. I can't draw a line that gives me a proper subprogram of more than one node that isn't the whole thing. So we call these guys primes. They're prime programs. And if it sounds like there's a theorem coming, there is. This guy at the bottom is not a prime because I can cut this line right here, cut this line right here, and now I have a proper subprogram that contains 2 nodes. So not a prime. So the key idea is that we have something that is analogous to the primes from number theory, right? Basically a program is composed of, is a composition of primes, or at least a proper program can be viewed as a composition of primes, okay? So an interesting question is, how many primes are there? In number theory, there's an infinite number of primes. If you ever take a number theory class, you will spend the whole time figuring out more and more convoluted and complex ways to prove that there's an infinite number of primes. And I suppose there's merit to that. There's a lot of common primes. They're the things you're used to seeing. If then else, while do, do until, do while do, which is a weird Ada-ism I don't want to get started on. I think it's also in PL1. Case statements and other stuff like that. And in a unsurprising twist, there's an infinite number of primes. Should not be a surprise. Should have seen that one coming. Infinite number of primes. What's the proof there's an infinite number of primes? It's this figure right here. Proof by picture. I love proof by picture. I draw this little guy and this little guy right here, right? Putting an F in here and then followed by this and that. I just repeat this as many times as I want. And I'll never be able to draw a box around something that cuts just a single entry and a single exit and gets me more than one, or gets the whole thing. Right? I can draw a thing around the whole thing, but that's the whole thing. I can draw it around this, but that's just a single node. If I tried anywhere else, I have to cut 2 arrows, either in or out. I just can't. 1 and then 2. And I can't make it happen. So, and I can repeat this once, and just connect it straight up, or twice, or 3 times, or 4 times, or any number of times. And each one of those is a new program prime. Infinite number of primes. So I can keep building structures until the cows came home. And so we might ask a question that people ask for a while, which is, can I get rid of goto? Right? I mean, people say that goto is harmful, but maybe I can't, maybe I have to have it. Maybe there's programs I can't write without goto. And this is a hard question to answer, but we can try to change it into a question that's easier to answer. So we can ask this: can any program with a set of structures be transformed into a program with just a few fixed structures? In other words, can I take my arbitrarily complicated program, like this thing over here, and rewrite it into something that only uses a few structures? That would be great. That would mean that I, the programmer, can learn a small set of things and just compose them together and be confident I can always build whatever program I need. That'd be great. That would be a fixed basis set, okay, of primes. Now we're breaking with number theory, right? Can I represent, is there a subset, a finite subset of the primes that gets me any integer? No, I got to have all of them, right? But there is, in other areas of math, there are finite basis sets. And if you're thinking about this in terms of logic, we can look for a finite functionally complete set. An example of that is and, or, and not form a functionally complete set for Boolean logic. And if that's too many, you can get rid of everything except NAND. NAND forms a functionally complete set. NOR forms a functionally complete set. So you can have them of different sizes. Is there such a set of program primes that is functionally complete? If there were, that would be kind of a neat little theorem. So one more key idea to introduce is a structured program. That's a program composed using a fixed finite basis set of program primes. So I tell you up front, you're allowed to use these primes. And I want you to build the program out of just these primes. And the question is there a set that will get you any program? And that's a kind of interesting theoretical computer science question. The allowable primes are themselves structured programs, and any composite built from just those primes will also be a structured program. So hopefully this makes sense, right? I start out with a prime, some kind. I replace a function node in that with another prime, and I replace a function node in that with another prime, and over time I build up a much, much larger program. The usual basis set is while do, if then else, and sequence. So, and you can imagine how this works, right? I write a while loop. The body of the while loop is an if then else. The then part is a sequence. The else part's another while loop. I'm composing the primes together to build the program. And the compelling question is this a sufficient functionally complete basis set? Can I write any program using just these three things? And the answer is no. I can't write any program using just these three things because I can only make this work if I have a proper program. So I need a single entry and a single exit, and then I'm in better shape. So we like to write programs with single entries and single exits, and because we can write them in a structured form, right? Think about how while do works. I come in at the top of the while loop, I exit at the bottom of the while loop and run the code that's next. Think about how if then else works, right? I come in at the top, I run some code, I exit at the bottom. Sequence, same thing, come in at the top, exit at the bottom, right? These are all single entry, single exit, proper programs. And if I build my program out of just those, I've built a proper program, sort of by definition. And it turns out proper programs have a lot of nice properties to them that we would like. And so we only want to write proper programs. So the question now, we can change it a little bit and we can say, can any proper program, including maybe this guy over here, be written as a composition of just these three? And the answer to that is yes. That's called the structure theorem. Every proper program is execution equivalent to a structured program composed from the basis set while do if then else in sequence, using only the functions and predicate nodes of the original program, along with tests and assignments to an additional variable that requires no more than the ceiling of the log of n bits. Wow, it's a lot to go at you. Ignore this last part. Basically, I use the original function and predicate nodes, and then I add this additional variable to it. And by doing that, I'm able to take any proper program, and there will be a structured program using just these three structures. Can I do better than three? Now we're getting into really abstruse computer science stuff, but yes, I can. I can do better than three. In fact, I can get down to one. There's a single structure that I can use to build any program. And if you're a Haskell nerd, you know what it is. If you're not, you don't want to know. So let's not worry about it. The proof of this theorem is constructive. In other words, the proof tells you how to take any proper program and turn it into a structured program using these three. Could I use more than those three? Sure. Of course I could, right? It doesn't matter if I use more than these three, right? But I can always get away with just these three. What does the proof look like? There we go. So step one, go to your program and give every node a number. Just start numbering them. For an assembly program, that's easy because they have addresses. So just give them just use their address. And so we divide the operations up into functions. There we go. And predicates. There we go. And sometimes we have to take an instruction and split it apart, but that's life. Then we take these little function nodes, right? The little function f says I do that, and then I go here. This says do p, and then go here or go here. And again, I've numbered the nodes. So this is node I. The next node pointed to by this is next. All right, so I don't have a nice little flow graph up here, but that's basically it. So I followed by next. And so for each one of these, I turn it into a little sequence. I say do f, and then set my counter. Remember, I had that additional counter in the additional label, we want to think of it as, set that to next. And this whole thing I can view as a single function f sub I. Single entry, single exit, like a little function, little tiny structured program. For predicates, I turn them into if then else's. Right? When it's true, this is a label of the next node in the sequence. When it's false, this is the label of it. And I just set the counter equal to whichever one of those it is. And then I gather back together over here and go out. So now I have an if then else, a little proper structured subprogram, which I can think of as a single node if I want to. Because again, single entry, single exit. The whole advantage of doing this is you can treat them as a thing all by itself. Once I've done this for all my function and predicate nodes, and that's all I have, I've done step 2. Now for step 3. Step 3 is not shown here, but I need to initialize the counter to the entry point's value. So if you just number them 1, 2, 3, 4, 5, starting with 1 at the entry, then you'd set the counter equal to 1 initially. If you have addresses, you would set it to the first address. The address is the entry point in your program. Initialize the counter. And then check to see if the counter is 0. And if it's 0, you terminate. If it's not 0, you go into a series of nested ifs or a case statement if you want to get fancy. It's just think of it as a series of nested ifs. And you see, is it 1? Is C 1? If it is, do the little program F1 that you created up here. If it's not, see if it's 2. If it is, do F2. If not, see if it's 3, and so on up through whatever n is. And what's going to happen is F1 is going to run. It's going to modify the counter. I go around here, and this tells me which one to do next. So really, I'm simulating the original control flow of the program, right? If the control flow was, do this followed by node 7, I would come in and do it, and then I would set C equal to 7. So next time around, I would do whatever I had for node 7. And I would just repeat this until I set C to 0 and terminate. And I would set C to 0 whenever I reach the exit line of my program, right? So I'll go back up here. Oh, yeah, here it is. Here it is. Assign the exit of the program the number 0. So whenever I had to exit, I would set C to 0 and I would exit. There you go. So here's my completed structured program. And why are we doing this? Why? It's easier to analyze a smaller set of program structures that can be understood in isolation than to try to analyze a strongly interconnected program. It just is. So if I can take a really nasty spaghetti code mess and I can turn it into a structured program, and I know I have just a small set of structures, I can write an analysis routine for sequences. I can write another one for if then else's, and I can write another one for, let's say, while loops, or for case statements, or for do until. And I can then analyze, I just look at what I have and I hand that off, analyze it, get a result back, and then I can plug that in to the larger structure and work my way up. And there's tons of tools that do that. If you plug your code into Ghidra, you'll see that it does a decompilation. And the decompilation is doing this stuff over here. It's extracting structure, or trying to extract structure, trying to discover the structure of your program so that it can then do further analysis, right? Because this is a tool to allow further analysis. We could also do this to obfuscate your program. And seriously, think about this. Suppose I just turn this into a giant case statement. I've got chaos now, right? I have some variable that's controlling where you go next. It can be chaos, right? So it can work either way. I can use it to build something, to take something nasty and turn it into something simpler to analyze, or I can turn around and use it to take a program that's nice and clean and break it into some chaotic looking mess, right? Either one of those will work. And in fact, people do this to obfuscate programs. It's just one of those little weird things that's fun. We did it on a tool called FX to analyze software. FX is now a commercial tool called Hyperion that's sold by a company called, used to be called Affirm Logic. I think it's called something else now. I can't remember. Anyway, they're out there hopefully selling tons and tons of the tool because I have some IP rights. An interesting question, another one of those fun theoretical computer science questions that turns out to actually have practical value is, can I eliminate the counter? And the answer is, I can. It's not always obvious, and there may be tricks as to how it gets eliminated. I may, in order to fully eliminate it, I might have to add more primes. And think about this. Suppose I could fully eliminate it, then I would have destroyed the distinction among certain kinds of primes. With that infinite prime I had, I can't turn that back into this other collection of primes without adding some information to it. I have to have the counter in there in order to simulate the original weird control flow. So I can't always eliminate the counter, but if my original program was a structured program in disguise, I can eliminate it. And enough I can. If I want to introduce new primes, I can always eliminate it. But if I'm not, then I can do it if the original program was sort of covertly structured. So if here's some stuff I would get. I get a little if then else, which says when it's true, do C2. What is C2? When I say C equal 2, I go around the loop again and I would do this. So why not just take this and plug it straight in here? Skip the middleman, skip the trip around the loop, and just put it right in here. And we did that down here. Same thing for the false branch with C is 3, and just plug that straight in. There you go. So I've taken this sequence of things and reduced it to this much, I think, simpler example. And there you go. So if I do that, this sort of broken up case logic gets reduced to something that looks more like a normal program. And in fact, this can make my program much more readable and useful. If I have a structure like this, so here's structure 1, it has a little predicate. If it's true, I do F and I set C equal to 4. If P is false, I do G and I set C equal to 1, which means next time around the loop, I would do this again. What I've got is an implicit loop, right? When C is 1, I come in and do this, and I set C back equal to 1, and I go on and do this again. So I'll keep doing this as long as P is false. So while P is false, I do G, and when it's true, I do F. I can turn that into this loop, right? P is false, do G. I'm sorry, yeah, if P is true, do G. I'm getting this wrong. If P is false, I get it right in a minute. If P is false, do G, right? Because not P is true. Do G. And then the minute that P becomes true and the not P becomes false, do F followed by setting C equal to 4. So I can take this and directly convert that into a little local loop. And I've exposed something about the structure of the program. It wasn't obvious immediately there was a loop up here. I can discover that and output it. And I can even find loops where I have multiple guys that reference each other and extract those. So structure theorem. Every proper program is execution equivalent to a structured program with while, do, if, then, else, and sequence using only the original program nodes and an additional counter to help me simulate the control flow. There were a number of attempts to prove this early on. Those early attempts lacked the notion of a proper program, and so they're a bit flawed. Harlan Mills came along and introduced the notion of a proper program, and I believe he gave, I think it's correct to say, he gives the first correct proof of this theorem. All right. As a my voice is running off the end, so as a final parting shot, let's talk about proper structured programs really quickly. Remember, a proper program has a single entry and a single exit, no trap or unreachable code. Is this stuff over here a proper program? Let's take a look at it. It's got a while loop, while 1. That sounds like a trap right there. It's a trap. No, it's not, because there is a return right in the middle of it. The return goes to our single exit, so it's fine. This is, in fact, a proper program. It's a structured program? Well, this looks like a while loop, but it's a while 1. That's weird. That's not really what we would think of as a while loop, is it? So we can debate about that, but it's definitely a proper program. What about this guy? So we come in here and we have this restart label, and we've got a go to and some other stuff. Is this a proper program? We come in at the top, we return here, we return here, return. Yeah, it's a proper program. It is. It may not look like it, but it definitely is. This is a proper program. Is it structured? Well, it's built out of some structures. Probably not the ones we want, but it's built out of some structures. If we say it has to be while, do, if, then, else, and sequence, then no, it's not, because you have this weird jumping out of the middle of something into the, no, it's not. So it's not structured in that sense, but it is a proper program. So it could be converted to a structured program if we wanted to. Here's some assembly. Is this a proper program? Is everything a proper program? Well, no, this is not. So here, this little stretch of code comes in. Sorry, we come in at the top, single entry, and we exit through here, or we exit through here. So there's 2 distinct exits two different destinations for our exit branch. So we are not a proper program. If we expanded the listing to reach these guys, we might eventually get a proper program. But as it stands right now, this is not a proper program, and it should be clear why it's not. So not everything is, but the things we'll encounter here will be. The point of a proper program is that it gives you all of the necessary context to be understood by itself. So imagine a program you write. You write the program and you analyze it and you know what it's supposed to do. But what happens at runtime is C bypasses a bunch of your code and jumps into the middle of it. It's not going to do what you want it to do anymore. It's going to do something different. The same thing is true for tricks like return-oriented programming, where I'm jumping into the middle of some piece of code in order to grab a ROP gadget. Right? In that case, it's stop doing what I want it to do. And so my analysis of the original code doesn't work anymore. Something else is happening. So because the proper program has a single entry and a single exit, it gives me all the context so that I can analyze it and understand what it does. It contains all of its reference. I know you come in at the top. I know you exit at the end. In between, I know what the code does. And so we think of it as being what we call referentially transparent, which means I can analyze that proper program by itself. I don't need to think about what's around it in order to analyze it. So if you want to reason about a program, especially if you want to write programs that analyze other programs, which we do, this is the important idea. What about this guy from the beginning? Remember him? Is that a proper program? Yep, sure is. Single entry, single exit. Yes, bytes get reinterpreted, doesn't matter. When I grab the ends and pull, it turns out it's just a straight up sequence, right? This jump 0 looks like a conditional branch, but it's really not. It's what's called an opaque predicate. Up here, I explicitly set the 0 flag, and then I jump. So this jump is always taken. Opaque predicate. The whole thing is one long sequence. So it's not structured here, but I can easily convert it to a structured program. In fact, it's just one long sequence. Nothing too elaborate. New homework. It's Wednesday, so there's new homework. And the new homework, which hopefully you'll be happy with, I don't know how you'll feel about it, is to do hello again. Yes, hello was such a rousing success last time. We're going to revisit it. Go back to your hello program and modify it so it does the following. I want you to correctly handle 0 as the first argument. If you're already handling 0, kudos, you've got that done. If you're not, fix it so it handles 0. I want you to issue the following error message if the first argument is negative. So here's an example, right? Hello, 0, Sue, and I say Sue 0 times. Success. Here I say hello minus 17 times to Sue, and it says no, you have to have a non-negative integer too. So there you go. So I want that error. I still want the old error. In fact, some of you don't write this error, write the correct text here, put the little error in front. I want you to correctly exit with 0 on success and 1 if you get an error. So up here we see I do hello with no arguments, and I echo the exit value, and you see it writes the message, and it says 1 because the exit value is 1. And the last proviso on this slide, the next one is, I want to be able to build this and link it as a position independent, dynamically linked executable. Okay? And using GCC would make it too easy, so you're not going to use GCC. I want your program to be written so it's directly started by a Linux. You will need an _start. So replace your main with _start. Where is argc? Where is argv? Those are on the stack now. So argc will now be at the top of the stack for you. argv0 will be immediately below it on the stack. or in terms of memory, immediately above it in memory. So below on the stack is above in memory. And this is how I'll build your program. I will NASM it, same as I did before, but then I will link it with the dynamic linker. And I'll say include the C runtime, or C library, not the C runtime, does not have the C runtime in it. Include the C standard library and make a position independent executable. Some hints, same hints as before, basically. Pay attention to the registers. Pay attention to the registers. If you get a seg fault, it's highly likely it's because you're misusing a register. If you use a Kali saved register, you usually have to save the old value and restore it before returning. For this assignment, you do not care about that. Why don't you care? Why would you not care about that? You had to care last time. Why don't you care this time? Think about that. It's worth understanding that. If you're using caller saved registers, assume that A to I and put S will screw them up. And so you may need to push and pop them like you did before. There you go. Next time we'll talk about basic blocks, structuring, and we'll start to learn Python because you can never learn too many programming languages. You can't be done. Can't be done. And we got done just as I was about to lose my voice and right at the 2-hour mark. So that worked out just great.